Okay, question 6. Hope you noticed to use PowerPoint this time because of my dodgy writing. Figure 10 shows the arrangement of some gears. Each gear turns around a fixed axle. Now, we haven't done this part yet. I've only just taught some of you gears. So it does not matter how many gears I put in between. All right. So it does not matter. In many ways, these are just idle gears. I could put 5 billion gears in between. The only thing that matters between this one turning and this one turning is the gear ratio between the first and the last. And that's what this question is saying. It says gear P's turn through 1 revolution per second. Well, they've got the same number of teeth. So 10 to 10 is the same as 1 to 1. And therefore, whatever this turns, this will turn the same. That's because this one will go anti-clockwise, that one will go clockwise, this one will go anti-clockwise, and that's it. So speed, it's a 1-to-1 ratio, so we're after 1, and the next one is, it's got to be the same as P as well, B. Okay, nice question this. We're now going to replace, so we're changing R, the 10 teeth, we're going to have a little rack. And what this is saying is this rack will be able to move up and down depending on whether we turn the gear. We use the driver going clockwise or anti-clockwise. It then says the teeth on the rack are 2 millimeters apart. So ultimately it says calculate how far the rack moves. Well, I know that every one tooth is going to equal 2 millimeters. Here I can see 10 teeth, 40 teeth. We know that this one will have more revolutions per minute than this one. So basic gear ratio 4 to 1. So the next part now is for every 4 turns of this, there's 1 turn of that. And then we can just whiz through what we're after. And it says how far when P goes through 1 complete revolution. So when it does 1 complete revolution, it's gone around 10 teeth. So Q will have turned 4 teeth. 4 times 2 is 8 millimeters. Job done. Next question. Now we've got turning moments, and again you've only had a single lesson on this just before we broke up, but I think most of you are quite happy with this actually. So use the principle of turning moments to calculate the mass of the toy elephant. So this is the idea that the turning moment or the system is in equilibrium, which it is. We can see it's all balanced, and it tells us the system is in equilibrium. So the principal moments, a system is in equilibrium if the turning moments of the clockwise turning moment is equal to the anti-clockwise turning moment. And what have I got to do? We need to find out the mass of the elephant. Phew. So I said to you, sometimes they'll make this tricky where you might have to turn the masses to weights, and we don't need to. I can just do rabbit times 15, duck times 10, add those two together. That will give me that turning moment, and we know that moody dinosaurs. If I want I'm going to change this F now to a mass. So if I want the mass equals whatever the turning moment of this side is, we'd move that across there, and we just divide it by this distance, 17. That's the basics. I'm going to delete all of this garbage, and now we're ready for a model example. So turning moment equals the force times the perpendicular distance. Now let's state it. So the anti-clockwise moment must equal the clockwise moment. Here is the anti-clockwise, here is the clockwise. And I've written it that way rather than the other way around because that links to the actual diagram. So on this side, I've done the rabbit. 6 times 15 is 90. I've taken the duck. 10 times 4.6 is 46. Added it together. That's now got to be moved over to here. So we've worked you out. So the next part now is, well, using our that's a force, or in this case we've got a mass, a moment and a distance. We're after U, so it's the 136 that we worked out divided by 17 8.0. And I did not leave it as 8 because we're still working on this. I want to express this answer to the same number of decimal places as they've given me in the question. So you can see it's 1 decimal place. I'm going to go to 1 decimal place. Okay, next one. We've got a metal tube is filled with oil. So again, you've not looked at this. This is idea of hydraulic pressure. So we've got this idea of hydraulics. We can see I've got a small area here, a large area here, and we need to know that the pressure equals the force over the area, which you'll have done lower down the school at Key Stage 3. And the basic idea for this is we can see we're pushing down on K and that force is L up. And the crucial part is, well, whatever the force divided by the area, that'll give me the pressure. This pressure will be transmitted in the liquid and it's the same all the way around. Now it's going to ask me about the force on L, where I can see F equals P times A. Well, if the pressure is the same all the way in this fluid, clearly what can I say? So the pressure here is the same as the pressure here. Well, if this area's gone up, the force must have gone up. And that's the basics. So explain the difference. Well, force K is going to be this force here is going to be less than this force. Next part, the pressure in the fluid from the K is the same throughout the system. And because we know F equals P times A, if L's got a larger area, then the force on L must be higher. Okay, and that's the basics for that. And I think that's that question all done.